Hello friends, we are step by step advancing in our Six Sigma journey, and right now we are in lecture 43, fractional factorial design, and I would like to remind you that we are basically at present discussing the improved phase of our DMAIC cycle of Six Sigma. So, we have talked about design of experiment and factorial design, and we have also seen the Minitab application of this. We have also seen the randomized complete block design, and now we want to advance with fractional factorial design. So, you may have a question that when factorial is there, what is the need of fraction? We will go to that, but let us try to appreciate this quote. A theory can be proved by experiment, but no path leads from experiments to the birth of a theory. Albert Einstein. We had seen as a recap that Minitab application of factorial design in the previous lecture, and now here we will talk about the concept of the fractional factorial design, alias structure, resolution, 1/2 2 raised to k design. There could be 1/4 2 raised to k design, but the procedure will remain same. We will just discuss the 1/2 2 raised to k design. Once you understand the design, the computation part, calculation part will be as it is, that we would not like to go into say discussion. So, we will basically try to appreciate the concept of fractional factorial design and what to do, what not to do, and remaining computation part will be as usual. So, now the question is that what is the need? When we have fractional factorial concept which allows us to extract as much information as possible about the main factor and the interaction of the factor, what is the need of going for a fraction when full gives me the lot of information? So, many a times you do not have adequate time, resource, budget. Now, we want to see that it is not only about conducting the experimentation. We talked about OFAT, one factor at a time, then we talked about the RCBD, then we are talking about the factorial design. So, it is not only important to conduct the experimentation, it is also important to conduct the experimentation in a smarter way. So, smarter way means the experimentation strategy which can help me to consume less amount of resources, whether time, material, manpower, and without compromising much with the inferences that I can draw from the experimentation and analysis. If I can do this, then I would be conducting my experimentation in a smarter way. So, here my issue is that I want to save upon my resources, and in what way I can conduct the experimentation using fractional factorial concept that can help me to achieve this less amount of utilization of resources without compromising much with the quality of the results. So, what is fractional factorial design? It is a type of factorial design. First thing is that known as the fractional factorial, because we are focusing on to find or focusing on vital few significant factors out of a large group of potential factors. So, many a times this is also called a screening experiment. I would like to focus on only few factors and I would like to screen it out. So, I do not have to say experiment with all the factors and all the possible interactions, but I can easily get a detail that what are the important factors that really needs to be considered for the investigation. Now, just see this and you will be extremely clear that why we are discussing this topic. So, let us say I have factor 1 and total number of runs per application is 2. So, how it is? So, let us say 2 raised to k. Here 2 is the level. I am considering 2 levels here. Let us say temperature 10 degree and 50 degree. So, I am considering 2 level, k is the number of factors. So, I am keeping the level 2 only. Now, let us see if I change the number of factor, you can say n or k, whatever you like to say. So if I change the number of factor n or k, then if it is 2, then 2 raised to 2 is 4. If it is 3, then 2 raised to 3 is 8. Now you just see, as I increase the number of factor, my n value, exponentially my total number of runs required per replication increases. So I would be investing a huge in conducting full factorial experiment with 2 raised to n or 2 raised to k strategy. Now if you look at little deeper, then the number of factors in 2 raised to n or 2 raised to k, where n or k refers to number of factors, increases, the number of runs required for a complete replicate of the design rapidly outgrows and resources are limited. Now if you look at the complete replicate of the 2 raised to 6, then 2 raised to 6 is 64 runs. It means I have to conduct the 64 runs to complete my full factorial design. Now in this design, 6 of the 63 degree of freedom correspond to main effects. So basically you have total 64 runs. If I just do -1, I will have total 63 degree of freedom. Out of this, only 6 are mainly specific to main effect, only 15 degree are specific to two factor interaction, 21 degree are likely to be degree of freedom associated with the effect that are likely to be of major interest, and 42 degree of freedom are associated with 3 factor or the higher order interaction. So typically this 21 means I say 15 plus 6, 6 is the main, 15 is the 2 level, and 42 would be 3 factor and higher order interaction. Now here the question is that, is it really necessary to analyze all the higher order interactions? And if yes, then obviously there is no other option, you have to go for full factorial design. But yes, if you can figure out that no, higher order interactions are not that much significant or that much important by some way through some logic, then you can reduce your experimental runs and hence the resources required for conducting the experimentation. So when typically the number of factors are more than 5, the total number of run 2 raised to n factorial experiment per replication is on the higher side, and it will be difficult to carry out all the runs for even one complete replication, forget about multiple replication, in order to achieve better accuracy of the experimentation. And this is where that I am concerned about the usage of the resources in conducting the experimentation. So here I would like to look at some other strategy like fractional factorial, and if fractional factorial can really help me to reduce my number of say experimental runs, then that would help me to save a lot on my consumption of resources. So just try to see why so many treatments. This table is very important, and it would be really interesting that you just see I am considering full factorial. It means I will analyze all the main and main effects as well as interaction effects. Just see the number of factors. Now suppose my number of factors are 2, then obviously main effects are 2, interaction effect is only 1 because there are 2 factors. Suppose number of factors are 3, main effect is 3, and you will have 3 2-level interaction and 1 3-level interaction. Very simple. Suppose you say A, B and C, these are the 3 factors. So I will have effect of factor A, I will have effect of factor B, effect of factor C. I can have the interaction effect AB 2 level, means 2 factor, BC and AC. So this is basically 3. So this 3 is 2 level interaction effect, and obviously ABC is the only 3 level interaction, so that is 1. Now likewise, you just try to analyze that what is happening. Suppose I go for more than 5, 6 factor, there would be 6 main effects to be analyzed or estimated, and then 15 2 level, 23 level, 15 4 level, 6 5 level, means 5 interaction, order interaction, and 1 is 6 because there are 6 factor. If you look at 10, you just see how many effects you will try to estimate. It outgrows exponentially, and it is extremely difficult to handle such an experiment where huge amount of resources, time, machine hours, operator, material is required, and you would not be able to really conduct your experimentation smartly, effectively. So now I have to do something to see that I can get rid of too much of the experimentation, trials, runs, and I can only focus on vital few which are really important to be analyzed. So there tends to be a redundancy in the full factorial design. So now the only solution is that you figure out what is the redundancy. If you can figure out this redundancy, you will automatically come down to estimating only those effects, main effect or interaction effect, which are really important, vital few, significant, and then you will just exclude all other interactions or effects from your list of estimation, and your number of trials, number of experimentation runs will drastically go down. So redundancy in terms of excess number of interaction that can be estimated, and fractional factorial design basically exploits this redundancy. So try to get rid of redundancy, your experimentation size will come down and you would be more effective in conducting your experimentation. But it's not just say terminating some of the effect estimation without any logic. So I want to teach you what is that logic by which you can really be reasonable, logical, scientifically true in reducing the size of the experimentation and can really focus on vital few. So how to figure out this redundancy? That is the issue that we want to address. Now, as I mentioned that a major use of fractional factorial is in screening experiment, and experiment in which many factors are considered, and the objective is to identify those factors, if any, that have large effects. So this is the screening experiments basically, and usually performed in the early stage of the project when many of the factors initially considered likely have little or no effect on the response. So for example, I will just say that I want to consider a response called productivity. Now I am just trying to put couple of factors as the main factors. Let us say factor A, skill level of the worker; factor B, state of the art technology or the efficiency of the machine; factor 3, layout of your plant; factor 4, moral of the worker; factor 5, top management policies in providing necessary resources. Now these are the factors. Now let us say if these are 5 factors, then 2 raised to 5, there would be 32 experimentation trials you have to conduct. Now let me try to see that all the interactions are really interesting to analyze. For example, moral of the worker and top management policy, yes, there could be a relationship, but efficiency of the machine and maybe let us say your worker moral, it may have an effect, it may not have an effect, or very not significant effect. Or you can say plant layout and maybe the state of the art technology. So technology is a different issue, plant layout is a different issue, interaction may not have any real value. So if you can really figure out that what are the interactions that are not really important, then this redundancy can be avoided and you can equip yourself in a smarter way for conducting the experimentation. So there are three important principles to be appreciated, and that creates the basis for fractional factorial design. So number one, the sparsity of effect principle. So when there are several variables, the system or product is likely to be driven primarily by, say, some of the main effects and low order interactions. So many higher order interactions, maybe 3 level, 4 level, you may say that they are not very much impacting my response, and this is the principle number one. Principle two, the projection property. So fractional factorial design can be projected into a stronger, larger design in the subset of the significant factors. So not that you have many factors, so your design is robust or design is stronger. Just think in a very simple way. I can set the analogy. You are purchasing a particular product like mobile. Now, do you think that this mobile will have thousands of features and that is why you would be happy? No, it's not necessary, because many features are redundant, you may not like it, or many times if the features they will interact with each other, they may not have any real effect on really your usage of the mobile, and then you would not like to pay for it. Same applies here, that stronger design does not mean I should have many factors, many interactions to be analyzed. Stronger design means getting rid of redundancy, having the relevant. The third principle is sequential experimentation. It is possible to combine the runs of two fractional factorials to construct the sequentially a large design to estimate the factor effects and the interaction effect. So you can partition your design, sequentially run it, and then you can better estimate the effects rather than conducting a full factorial design in one go. So 1/2 fractional factorial design, you can also express it as 2 raised to k minus 1. So just see with the example, suppose if I say 2 is the level, this is the level, these are the factors, and if I say this is my 2 level 5 factor full factorial, I will have 32. Now if I say 2 raised to k minus 1, which refers to 1/2 fractional factorial design, so 2 raised to 5 minus 1 is equal to 2 raised to 4 is 16. So this is exactly half of 32, and that is why it is called 1/2 fraction of the 2 raised to k design. It means I would be actually conducting only 16 experimental runs to reach to more or less the same conclusion which otherwise I would reach through full factorial design by conducting all 32. So this is what I am trying to do as a part of my fractional factorial, and this is exactly what I explained here. Now let us see that how your experimentation look like. So this is the treatment combination. So you have A, B, C, ABC, AB, AC, BC and 1. You have something called I. So this is my identity column, and just I am introducing it. I have A, I have B, I have C, AB, AC, BC and ABC. Now let us try to appreciate that how we will read this table. So when I say that my factor A, you just see initially it is set at plus, means the high level, and then 2 times it is low. Then it is set plus plus plus, then again it is low, low. I have set B at low level, then I have set plus, then I have set low, then again I am setting it twice high level, low, high, low. You can see here low, low, high, and then this is high. So now what exactly you can see that when you try to develop a table, you must see, I am telling very important point, it is not about plus and minus. When you have 3 factors A, B and C, and you are setting it at high level or low level and then changing it in the next experimental run, please try to understand that it is not only about changing the factors of changing the levels of the factors, there is a cost associated. For example, a factor which is very difficult to set or change, if you are changing it frequently, it will have a great impact on your response, or the setup time would be very large, and this kind of approach would not be good. So let us say once again, if I see A is changed first plus and then it is kept minus and minus. Now you see there is only one time change. If you see this is set minus, then again change and again change, 2 times change. This is only one time change if I just refer up to here. So you can say that the factor which is most difficult to change should be changed less, and hence you do not frequently change from low to high and high to low. So A, B, C is just the generic term alphabet. You need to assign the factors and assign the factors in such a way that the factor which are easy to change may accept frequent change, the factor which are difficult to change or has a negative or adverse effect on your response, they should be assigned to the column which has less frequent changes in the level. So I hope it is clear. Now you can see here that I have AB. So this is nothing but the multiplication of plus and minus. So this is AB, AC. So this A plus minus, this is minus, BC, both are minus, this is plus, and this is how you construct this particular table. So this table basically is about the strategy in what way I will conduct the experimentation, and this is the table of 2 raised to 3 full factorial. So 2 raised to 3 is 8. So it is full factorial. I am trying to estimate all the main effect and the interaction effect. You can see here main effect A, main effect B, C, ABC, AB, BC and AC, AC and BC, and this is the initial setting. So where all the factors are set at the low level. So this is what you can appreciate about the. Now you just see here in a particular form that this is the principal fraction I is equal to ABC plus ABC, and this is the alternate fraction, that is I is equal to minus ABC. You have the initial condition here. So the design which I had shown in the previous table now could be divided into 2 fractions, that is positive plus ABC and minus ABC. So I can go back to help you to appreciate this, that you just see this, you have plus plus plus, you have minus minus minus. So you have 2 say separate fractions to be analyzed. Now let us see that what is actually happening. Now there are some basic principles when we want to appreciate the fractional factorial design and how to get off the redundancy. So typically say you have the treatment combination A, B, C and ABC as our 1/2 fraction, and these runs are shown in the top half of the table as I have shown with plus plus plus. Now 2 raised to 3 minus 1 design is formed by selecting only those treatment combination, let us say they have plus 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 sign in ABC column, and ABC typically called is a generator. So I am just trying to introduce a term, technical term, it is a generator. Now when I try to equate I is equal to ABC, then I am calling this as a defining relationship, and this defining relationship will help me to identify the redundancy in conducting my full factorial experimentation, and hence to reduce the size of my experimentation as a part of fractional factorial. So remember that I am defining the relationship in terms of say generator and the identity column I is equal to ABC, because I have 3 factor factorial design. Now let us see how we use it for identifying the redundancy. Now if I estimate effect A, B and C, this is really interesting to see what is coming here, A minus B plus C, A minus B minus C plus ABC. Let us see how it is. So I will just go back, just see here that I am estimating A, and you are referring this particular table, you are referring the half. So just see A into plus is plus A, B into minus is minus B, C into minus is minus C, and ABC into plus is plus ABC. So A minus B minus C plus ABC you got, and just try to verify whether it is true or not. Yes, it is there, and this is for averaging out 1/2. A minus B minus C plus ABC. Same way you can estimate B and C. Now just try to see BC, A minus B minus C plus ABC. Let me go back again to help you. If you look at this particular, then suppose if I look at this, then minus A minus B plus minus A minus B to estimate this interaction plus C plus ABC. If you look at BC, then it is plus A minus B minus C and plus ABC. So this is how I am just trying to estimate the effects. Now what you can see here, something interesting, that if you see the A and BC, then their expressions are same. If you see B and AC, the expressions are same. If you see C and AB, their expressions are same. So this means that when you are estimating A, actually you are not estimating A, but you are estimating A and BC. When you are estimating B, main effect, you are actually not estimating B, you are estimating B and AC, and similarly C, you are estimating C and AB. So this is typically called aliasing of the effects or confounding of the effects. It means that some of the effects are aliased or confounded with some of the effects, and higher order interactions are confounded with either the main effect or lower level interaction, and hence this is the redundancy which can be avoided in conducting the experimentation. So this is the key point, and I hope you have appreciated. So exactly this is what I have explained, that A is equal to BC, B is equal to AC, C is equal to AB, and I can use my defining relationship also to conduct the same analysis. So let us say I have defining relationship I is equal to ABC for 3 factor A, B and C. Let me multiply both the sides with B. So you see it is A B square C. So B square is nothing but entire column is squared, so this become identity. So basically you have B is equal to AC, and this is exactly what we have seen. B is equal to AC, similar way C is equal to AC. So these effects are confounded with the main effects AC and AB, and really when I am estimating the main effect, within that the estimation of this effect is included, and there is no need to separately estimate these effects. Thus this is the redundancy in full factorial design that we should try to avoid. Now there is another concept which is very important in fractional factorial design. When I am only working with the fraction of the trial number of runs, by getting rid of the redundancy, by identifying the aliasing or confounding effects, I also need to look at the resolution. Resolution means the accuracy in judging the effects. So this is an important property, and basically it indicates the ability to separate main effects and the lower order interaction from one another. So typically in fractional factorial approach, design of high resolutions are better, and that can provide more information. So there are 3 different types of resolution. Typically we refer resolution 1 and 2 do not add much value. So typically we refer resolution 3, 4 and 5. So resolution 3 design means it is a design in which main effects are aliased or confounded with any other main effect, no main effects rather are confounded with the main effect. So there is no confounding of the main effect, but main effects are aliased with 2 factor interaction, and some 2 factor interactions may be aliased with each other. So this is typically a resolution 3 design and expressed as resolution 3 design. Similar way resolution 4 design, the condition is that no main effect is aliased with any other main effect or with any 2 factor interaction. Even 2 factor interactions are not aliased, but 2 factor interactions are aliased with each other. This is expressed as resolution 4 design. For resolution 5 design, no main effects or two-level interaction is aliased with any other main effect or two-level interaction but two-factor interaction, but two-factor interactions are aliased with three-factor, and this is called resolution 5 design. So please keep in mind that there are various resolutions when you talk about fractional factorial design, and you can analyze the design matrix. Just another example for 2 raised to 4 minus 1 factorial design, fractional factorial design. If I conduct the 2 raised to 4, then I have to conduct 16. When I go for 2 raised to 4 minus 1, I have to conduct basically only 8 experimental runs. So here it is 8 experimental runs. See the setting of A, B, AB, C, AC, BC. Basically once you have set A, B, C, other are just derived by the multiplication. So minus 1 into minus 1 is plus 1, minus 1, plus 1 into minus 1 is minus 1, and so on. So this is the table, initial table. Now I am just trying to analyze the aliasing. So I have defining relation I is equal to ABCD. I can multiply both the sides by A, multiply A, and what you will get here is this. So you get BCD. So you have basically A is equal to BCD. Similar way, B is equal to ACD, C is equal to ABD. It means your aliasing, confounding of this three interaction effect, three factor interaction effect is taking place with the main effect, and this is where the redundancy exists. So similar way you can do it. Aliasing structure for all two factor interaction. You define the relationship, multiply them by the same two level interaction. So you have I into AB multiplied also by AB. So this will become your I. So you have basically CD. You multiply this by AC, A square, C square, this becomes I. So AC is equal to BD, BC is equal to AD, and so on. So I hope the idea is clear. Similar way for three factor, multiply your defining relationship I is equal to ABCD by three factor ABC, ABD, ACD, BCD, and you will get the structure. So in summary, you can say that you have the effects, you have the aliases, and typically these aliases are basically confounded or aliased with these effects, and there is no point in separately estimating them. It just creates the redundancy. So with this, I would like to float couple of think it for your introspection and to go deeper into the concept. So why fractional factorial designs are preferred over full factorial design? What is resolution and alias structure in fractional factorial design? Just give a thought and the idea would be clear. The rest of the computation will follow the same procedure as we did for the factorial design, and you need not to say bother much about the calculation part. You can also use the Minitab and you can follow the calculation. So these are the references. Basically, typically you refer Douglas, Montgomery for design of experiment, and that would really help you to appreciate the concept. So fractional factorial helps us to conduct the experimentation in an effective way, smarter way, by saving our resources, and it's a more practical, feasible approach for conducting the experimentation. So thank you very much for your interest in learning the concept of fractional factorial, and I hope this video will definitely help you to appreciate the importance of fractional factorial and how to get rid of some of the redundancy present in the factorial design. So please keep revising, solve a couple of examples to gain deeper insight. Thank you very much. Be with me. Enjoy.